Good morning to all of you. We were discussing magnetization in materials. So, let us recall that if you place a medium in a magnetic field, that magnetic field induces magnetic dipoles or magnetizes the material, and the magnetized material consists of a large number of tiny magnetic dipoles, and these magnetic dipoles then generate their own magnetic field. So, if you place a material in a magnetic field, then the magnetic field gets altered, and we are trying to discuss how do we incorporate this and calculate the magnetic field in the presence of material. The problem is very similar to what we had done in electrostatics, where we had looked at the problem of putting a dielectric inside an electric field. So, when you place a dielectric inside an electric field, the electric field polarizes the medium, that means makes tiny electric dipoles in the medium, and those tiny dipoles then generate their own electric fields, and the total electric field that you observe is the sum of the electric field that you are applying and the electric field generated by the tiny dipoles. In a very similar fashion, when you place a medium in a magnetic field, the external magnetic field magnetizes the medium, and magnetized medium generates its own magnetic field, and the magnetic field that you measure or you observe is the sum total of the magnetic field that you have applied and the magnetic field generated by the magnetized medium. So, we started to look at how do I represent a magnetized medium and how do I calculate what is the field generated by a magnetized medium. So, let me recall that if you look at, if you take a, so we are looking at magnetization. So, we have seen that if you take a cylinder like this, magnetized in this direction parallel to the axis, then this magnetization, that means it is magnetized, meaning that magnetization is magnetic dipole moment per unit volume. That means you take a small tiny volume of the material, that tiny volume is small compared to the size of the material, but contains a large number of atoms, and that tiny volume will have a certain magnetic moment, which is the sum of the magnetic moments of all the individual particles within that volume. Then that magnetic moment divided by the volume will give me the magnetic dipole moment per unit volume, which is nothing but magnetization, which is represented by capital M vector. So, if you have a medium like this which is magnetized parallel to the axis, we had seen that this is equivalent to having a surface current given by, so this is equivalent to a surface current per unit length of M. Now, the direction of the surface current as I have drawn here is like this, perpendicular to the magnetic field, magnetization sorry, and this magnetic the current per unit length is nothing but M. So, if you take a length T here, the total surface current on this surface would be N times T. So, we had looked at this and found this magnetization. So, now let me look at, so how do I what is the effect of this kind of medium on an Ampere's law? So, we started looking at a solenoid. So, let me look at again a solenoid which has which is so this is a solenoid, there is the medium here, and I wind wires on this. So, I have wires wound on a medium, and this wire is carrying current like this. So, there are currents propagating like this, each of the wire is carrying the same current just like a solenoid, except that now this is a medium. So, I have a current I flowing through the current through the wires of the solenoid. Now, what is the Ampere's law? Ampere's law tells me integral B dot dl is equal to mu 0 times current enclosed. Integral B dot dl, where B is the magnetic field, is equal to mu naught into I enclosed. Now this, so when I have this medium and pass a current, the current generates a magnetic field and that magnetic field will magnetize this medium, and in this case the current produces a magnetic field which is pointing along the z axis, and the magnetization will also be parallel to the z axis. So, let me assume that the magnetization is something like this here. So, if I look at this here, so I essentially have a medium which is magnetized in the vertical direction and the magnetic field produced by the external current is also in the vertical direction. Now, I apply this Ampere's law. So, what I do is I take a loop of length L and integrate over this path. So, I take a Amperean loop crossing the solenoid and inside the material here and apply the Ampere's law. Now, what is the current enclosed? Please note that there are two components to current enclosed. One is the current that I am passing through the wire, which is I, and the other is the current which is represented by the magnetization itself. So, the magnetization is equivalent to a surface current. So, on this, within this loop, the current crossing consists of I enclosed consists of the current which I am passing through the wire, and if the number of turns per unit length is n is the number of turns per unit length, then the current enclosed will have n times I times L. There are n L loops current crossing the path and each of them has a current I, and also I have magnetization. So, magnetization is equivalent to a surface current passing in the same direction as this current, and magnetization, which is the current per unit length, times L will be the current due to the magnetization. So, I enclosed now consists of two components. One is the current, actual current passing through the wire, which is called the conduction current, which is actually electrons are moving from one end to the other end passing through the wire. The other is what is called the bound current, that means current which is consisting of atoms circulating electrons within each of the atoms in the material. So, that current is represented by magnetization, and so the total current enclosed is given by NIL plus ML. So, Ampere's law gives me B dot dl is equal to mu 0 times NIL plus ML. So, the current enclosed has conduction current plus the current due to magnetization, which is represented by surface current. So, I am assuming here that the material gets uniformly magnetized and that uniform magnetization generates a surface current given by m times L within the length L. Now, let me try to calculate this quantity integral m dot dl over the same loop. Now, remember, outside the solenoid there is no magnetization because there is no medium. So, on this part of the loop, then integral will give me 0. On this part, on these parts which are outside the solenoid, again m is 0. So, there is no contribution to the integral. On these two parts which are lying within the medium, m is perpendicular to dl, because m is vertical and dl is at this in the perpendicular direction. So, m dot dl contribution from here and from here becomes 0, and the only contribution comes from this part of the loop, and along this length magnetization will be independent of position because of the symmetry of the problem. So, this will be simply equal to m times L, where m is the value of magnetization at this point times the length, because there is no contribution to the integral from the remaining 3 parts of the closed circuit. So, I can write this m L as integral this thing. So, let me divide by mu naught both sides. So, I get integral b by mu naught dot dl is equal to n I L plus integral m dot dl. I have replaced m L by integral m dot dl. So, let me take integral m dot dl to the left hand side. So, I will get the following: integral b by mu naught minus m dot dl is equal to NIL. Okay, what I have done essentially is taken m dot dl to the left hand side. So, B by mu naught minus m dot dl will be equal to NIL. Now, as in the last lecture, I introduced a new vector called H vector, which is B by mu naught minus m. This is the defining equation for a vector H. Remember, in electrostatics, I had introduced a vector called D vector, displacement vector, which was related to the electric field and the polarization, epsilon 0 E plus B is equal to D. Similarly, I introduced a new vector called H vector, which is B by mu naught minus m. So, this equation simply gives me H dot dl is equal to NIL. And what is NIL? NIL is nothing but the free current passing through this loop. The current which I am passing through the wire, the conduction current which is passing, which is called the free current. The conduction current passing through the loop is the only one which is crossing this. So, the right hand side is simply equal to IF enclosed, where IF enclosed is equal to free current enclosed by the loop. So, I get a new form of Ampere's law, integral H dot dl is equal to I free enclosed. This is again Ampere's law. Which is valid in the presence of material. Now, the advantage of this equation, if this kind of an equation, is that on the right hand side I only have free currents which are existing. That means, the current which I am passing through the wires, and all the properties of the material are contained in the defining equation for H, which is magnetization essentially. So, H is equal to B by mu naught minus m. The properties of the medium are contained in m, and so H contains the properties of the medium, and the free charge enclosed is on the right hand side, the free currents enclosed. Now, this equation is similar to the modification of Gauss's law, which we discussed in terms of displacement vector. I showed you at that time that the modified form of Gauss's law is very helpful in the presence of material, especially when there are symmetries. Similarly, this equation, this form of Ampere's law is very useful, especially in the presence of symmetries, because if I need to know only the free currents in the circuit, and if I use symmetry to take H out of this integral, then I will be able to calculate H vector, and from H vector I should be able to calculate all other quantities like magnetic field, magnetization, and so on and so forth. So, this is a very, very useful form of Ampere's law. Now, I must mention here, although I have derived this equation for the case of a solenoid wire wound on a material, this equation is a very general law. It is valid in general and is a modified form of Ampere's law, which contains H vector instead of B vector, and H vector's definition is B by mu naught minus m. So, this is the definition of H vector. Now, for a large class of materials, the magnetization is proportional to the H vector. For a large class of materials, the magnetization is proportional to H, and chi m is the proportionality constant, which is called the magnetic susceptibility. Remember, we had introduced the electric susceptibility in electrostatics. Similarly, we have a magnetic susceptibility in magnetostatics, which is the proportionality constant between m and h. Now, this is for a large class of materials that m is proportional to h, and such media are also called as linear media. Because m is proportional to h, the relationship between m and h is linear. They are also called linear media, and this is a linear relationship, and there is a large class of materials which belong to this. One of the example is diamagnetic materials. Now, diamagnetic materials have a chi m which is less than 0, and paramagnetic materials which has chi m greater than 0, and in both these materials the value of chi m is much less than 1. In both diamagnetic and paramagnetic materials, this value of susceptibility is very small compared to 1. Now, there is the third class of materials, ferromagnetic, in which the magnetization is not proportional to H. I will come to a discussion of ferromagnetic materials a little later, and also the diamagnetic and paramagnetic materials, the materials themselves, but right now I want to emphasize that for media, for a major class of media which are diamagnetic or paramagnetic materials, the magnetization is proportional to the H vector, and the relationship is written as m is equal to chi m times H. So, if I use this equation for m in this equation, so I want to use m is equal to chi m H in this equation, so I will get the following equation. So, I had this equation, let me rewrite. H is equal to, I had defining equation B by mu naught minus m. So, this tells me B is equal to mu naught into H plus m, and I am replacing m by chi m times H. So, B becomes mu naught into 1 plus chi m into H. And this is written usually as mu times H, where mu is equal to mu naught into 1 plus chi m. Now, what is mu naught? We have introduced long time back. Mu naught is the permeability of free space, and mu is called the permeability of the medium. So, the medium properties are represented in mu, the magnetic properties of the medium are represented by mu, the magnetic permeability of the medium. It is similar to the dielectric constant and the dielectric permittivity of the medium that we had introduced in electrostatics. Similarly, we have mu naught as the permeability of free space, mu is the permeability of the medium, which is given by mu naught into 1 plus chi m. So, it depends on the susceptibility, and as I mentioned before, since for dia and paramagnetic materials chi m is much less than 1. So, for diamagnetic and paramagnetic materials, chi m is much less than 1. So, mu naught is approximately equal to mu, sorry, mu is equal to approximately mu naught. And actually for diamagnetic, chi m is less than 0, this implies mu is less than mu naught, and for paramagnetic chi m is greater than 0, this implies mu is greater than mu naught, approximately equal to mu naught, but slightly greater than mu naught for paramagnetic, slightly less than mu naught for diamagnetic, because diamagnetic have chi m as negative. So, the value of mu is slightly less than mu naught for diamagnetic, mu is slightly more than mu naught for paramagnetic materials. So, we have defined a permeability mu. We can also define a relative permeability K m is equal to mu by mu naught, which is equal to 1 plus chi m. This is the relative permeability of the medium, just like relative permittivity, which was called the dielectric constant in electrostatics. Here we have a relative permeability which is mu by mu naught, and for paramagnetic and diamagnetic materials, this relative permeability is very close to 1. We will discuss ferromagnetic materials slightly later in more details, and also diamagnetic and paramagnetic, and you will appreciate that in ferromagnetic materials the permeability definition itself is to be discuss a little carefully. So, what we see is that there are, when you place a medium in a magnetic field, external magnetic field, that external magnetic field magnetizes the medium, the magnetized medium then generates its magnetic field, and the total magnetic field gets altered because of magnetization. Now, let me give you a table of typical values of chi m for diamagnetic and paramagnetic materials. So, chi m for dia and paramagnetic. Some examples. To give you an idea of the values here, so let me look at a table for diamagnetic. So, bismuth minus 16.4 into 10 to the minus 5. So, this is chi m. Copper is minus 0.98 10 to the minus 5. Diamond minus 2.2 10 to the minus 5. Gold minus 3.5 10 to the minus 5. Silver minus 2.4 10 to the minus 5. Water minus 0.9 10 to the minus 5. So, as you can see here, the susceptibility is very small, and so mu is approximately mu 0, and all the susceptibility values are negative. These are diamagnetic material examples, and I will give you some examples for paramagnetic materials. Aluminum, so this is chi m here, 2.1 10 to the power minus 5. Platinum 26 10 to the minus 5. Magnesium 1.2 10 to the minus 5. Tungsten 6.8 10 to the minus 5. Uranium 40 10 to the minus 5. Oxygen 190 10 to the minus 8. Gadolinium 48 10 to the minus 2. So, these are again some examples of paramagnetic materials, and you can see here typically the susceptibility values are much smaller than 1, and so for both diamagnetic and paramagnetic materials, the value of permeability is very close to permeability for free space, and in most calculations of electromagnetics, people will assume that mu is equal to mu naught typically in these materials, in dia and paramagnetic materials. In ferromagnetic materials, the story is very different, and when we discuss properties of materials specifically, we will be able to appreciate the large difference in the permeability between ferromagnetic and diamagnetic paramagnetic materials. Ferromagnetic materials, of course, all of you know, these are iron etc., which form permanent magnets, and they have a very strong magnetic field even in the absence of magnetization, even in the absence of an external magnetic field. So, we will discuss the three diamagnetic, paramagnetic and ferromagnetic materials in a little more detail after we discuss an example. So, I want to consider one example of using the modified form of Ampere's law to show you that it is possible to calculate the magnetic field, the magnetization etc., in a problem in which there is material within the system. So, the example which I want to look at is the following. I have a dielectric cylinder here, and I am passing current in a solenoid. So, this is the wires of the solenoid. So, I am going to assume that the system is infinitely long. So, this is the wire which is carrying the current. So, let me draw a side view. So, this will be the cylinder here. So, the side view will look something like this. So, I have the material here, current is coming out from on this side through the wires, and the current is going back into the page from the other side. So, current is coming up from here, going in here, and this is the material. So, now in the earlier example I had assumed that the material was filling the entire solenoid. Now, what happens if the material does not fill the entire solenoid, but the material is only part of the solenoid? So, as I have drawn here, I have a solenoid which has a winding, and again let me assume n is the number of turns per unit length, and I is the current. Through the wire. So, I want to calculate the magnetic field inside the material. So, this is the material here. So, this material has chi m, susceptibility chi m, magnetic susceptibility chi m, and outside it is free space. So, here it is 1 and outside it is sorry, chi m is 0 everywhere else except in the medium. So, mu is mu naught here, mu is mu naught here, mu is mu naught into 1 plus chi m here, mu is equal to mu naught outside. So, I want to calculate what is the magnetic field inside and outside this medium in the solenoid. Now, first thing that we notice is that the moment I pass the current, the magnetic field generated by the current in the solenoid is in this direction. So, this is the z direction. So, magnetic field will be in this direction everywhere inside the solenoid. Of course, outside the solenoid there is no magnetic field, as we have seen before. For an infinitely long solenoid, the magnetic field outside is 0. So, magnetic field is generated inside. Now, this magnetic field is going to magnetize this medium and with a magnetization in this direction. So, the magnetic field generated by the current carrying conductor magnetizes the medium, which then has a magnetization in the vertical direction, and this magnetization, as we have seen, is equivalent to current passing through the surface of this material. Now, I want to use this modified form of Ampere's law, H dot dl is equal to I free enclosed. That is the Ampere's law which I want to use to calculate H vector everywhere, because this equation is in terms of H vector. I will calculate H vector everywhere, and from H vector I will be able to calculate the V vector. So, now let me draw this figure again. So, this is the inside material and my current carrying conductor is here. Now, I want to take a loop like this for calculating this integral. This is my integral H dot dl I free enclosed. Now, to do this I need to take a loop. So, first let me take two loops, one is this loop and another is this loop. C1, C2, and remember the B field is like this, M field is like this, and H field will also be like this. So, H is B by mu naught, H is equal to minus M, and B is equal to mu naught into 1 plus okay. So, this equation we had derived earlier, these two equations we had obtained earlier. Here are the equations: B is equal to mu naught into 1 plus chi m into H, and H is B by mu naught minus M. So, this is what I have written again. Now, for path C1, so of course, there is a magnetic field here also. this is the magnetic field everywhere is within the solenoid. So, in this path does not enter the medium. I know the magnetic field to be along the z direction. So, this is the z direction here, upward direction is z direction. The magnetic field is parallel to z axis. There is no magnetic field outside. So, integral over path, this path is 0. Integral over this path is 0 because magnetic field is perpendicular to this path. In fact, there is no contribution from the here and here because there is no magnetic field, but over this path of this part of the path which lies inside the solenoid, B vector is perpendicular to dl vector. So, there is no contribution from here. H vector is also perpendicular to the path. So, there is no contribution to the integral from here and here. So, if H is the H field here, so this equation, this integral tells me H into L, if L is this length, is equal to, now what is the current enclosed? N number of, so there are current wires crossing this. So, this is N times I times L. The number of loops crossing this path is N times L because N is the number of turns per unit length. So, N times length is the number of loops crossing this path. Each of these paths carries a current I. So, the total current passing is N I. So, H is equal to N I, and in vector form H vector is equal to N I K cap. So, this is the magnetic, this is the H vector in the region between this region. So, let me call so the region between the wires of the solenoid and the medium, this is the H vector. So, that gives me the H vector here. So, what I find is if this is the and in this region H is equal to because this path has actually in this region. So, I am calculating the H vector in this region. Now, let me calculate for path C2. Now, look here for path C2 again I apply the same law. There is no H vector outside. So, there is no contribution from here and from these two parts of the path. For these two parts of the path, H vector which is along z direction is perpendicular to dl vector. So, there is no contribution from these two paths either. So, only contribution is coming from this path. So, if H is the H vector here, I will find H is equal. So, if I call H as so let me call it H prime here. So, if H prime is the H vector within the medium, so for path C2 I apply the same equation H dot dl is equal to I free enclosed. So, I will get H prime into L is equal to what is the total current enclosed. Now, please remember in the right hand side of this equation I only have the free current, the conduction current, the current that I am passing through the wire. This path contains bound currents, but bound currents do not enter on the right hand side here. The right hand side only contains the free currents. So, I have to only bother about the free currents on the right hand side. The bound currents are already contained in the H vector because bound currents are contained in M vector, which is actually contained as a part of H vector. So, free current is the one which I have to bother about for the right hand side, and the free current passing through the length L again, if this length L is the same as before, which is equal to N I L. So, this is equal to N I L, which implies H prime is equal to N I and H prime vector is equal to N I k, which is also equal to H vector. H vector is N I k, H prime is N I k. So, what is happening is, so if this is the material here, these are the wires of the solenoid. Here H is equal to N I k, here H is the same. So, H is the same throughout the region of the solenoid, within the solenoid, and of course, H is 0 outside. So, H vector is equal to N I k everywhere within the So, H vector here, here, everywhere is the same within the solenoid, outside the solenoid H vector is 0. So, without knowing anything about the property of the medium, without knowing anything about the surface currents, bound currents, etc., I have been able to calculate H vector. Now, this has been made possible because I knew that by symmetry arguments B vector is vertical, M vector is vertical, H vector is vertical, and B is 0 outside, M is 0 outside, H is 0 outside, etc. So, all these arguments which I had used to get the magnetic field of a solenoid based on symmetry arguments are still valid, and that has helped me to do this integration on the left hand side in spite of the fact that I did not know exactly the value of H, and that has helped me to find out the H vector within the solenoid and outside the solenoid for this problem. So, H vector is the same whether you are within the medium here within this medium or outside the medium, as long as you are within the solenoid H vector is the same. Now, I know the relationship between H vector and B vector. B is equal to mu naught into 1 plus chi m into H. So, the medium which I am putting inside I am assuming to be linear, to be related to have an equation m is equal to chi m h, which I had introduced. So, B is equal to mu naught into chi m h. So, I need to calculate now. What I need to calculate is the magnetic field here, here, and of course, the magnetic field outside is 0, B is outside 0. So, I need to calculate what is the B vector within the material of the solenoid, within the material here, and between the material and the wires of the solenoid. So, let me draw again. So, this is the medium, here are the wires. So, let me call this region 1 and this is region 2. So, in region 1 chi m is 0 because there is no medium. This region 1 also includes this part. These are the same reasons, because remember this is the material and the wires are going like this. Okay, so, this entire thing outside this cylinder is actually within the solenoid is region 1. So, B is equal to mu naught H, which is equal to mu naught N I. So, magnetic field in this region is mu naught N I k, and please recall the discussion in solenoid, it is the same as if there was no medium inside. For this problem, because of symmetry, it so happens that the magnetic field here B vector here is the same as if there was no material here. Now, why is this happening in spite of the fact that there is a material inside? The reason is the following. Please remember, the material is magnetized because of the magnetic field. The magnetization of this material is like this. This magnetization is equivalent to surface currents like this. This surface current is equivalent to a solenoid, which is this solenoid, and that solenoid has no magnetic field outside. Let me give you the argument again. How is it that the magnetic field in this region, region 1, happens to be the same as the magnetic field in the absence of the material? This is so because of the following argument. When I pass a current through the solenoid, that current magnetizes the material. That magnetization of the material is along the z axis. This magnetization leads to, if is effectively equivalent to surface current on the surface of this material, which is going like this current. This surface current is equivalent to a solenoid of this dimension, and this dimension of solenoid does not produce a magnetic field outside its dimension, and so the magnetic field here is primarily generated only by these currents and not by these currents. And so the magnetic field here is the same as if there was no material. Now, what about region 2? Region 2, B is equal to mu naught into 1 plus chi m into H. which is equal to mu naught 1 plus chi m, H is Ni times, and this is also equal to mu times Ni. So, all that has happened is magnetization inside has changed the magnetic field within the medium to mu times Nik. The magnetic field outside is mu naught Nik. So, magnetic field inside the material is different from the magnetic field outside, and it depends on this difference between mu and mu naught. Of course, for paramagnetic and diamagnetic, mu is very close to mu naught. So, the magnetic field inside the material and outside the material are almost equal to each other, but they are slightly different. Now, it is also interesting to note that for diamagnetic materials, chi m is negative, which means that mu is less than mu naught, which means the magnetic field inside the material is slightly less than the magnetic field outside. Because mu is less than mu naught, chi m is negative. So, the magnetic field inside the material for a diamagnetic material here is slightly less than the magnetic field outside. For paramagnetic materials, chi m is positive, mu is bigger than mu naught. So, magnetic field inside the material is slightly more than the magnetic field outside. So, the presence of the material modifies the magnetic fields in different parts, and in this problem which has a lot of symmetry, we have been able to use the modified form of Ampere's law to calculate the magnetic field everywhere. In fact, we can also calculate the magnetization of this medium. Magnetization, we remember, is chi m into H, which is equal to chi m Ni k. So, we have got the magnetization here. Now, you see here for diamagnetic chi m is negative. So, let me draw the figure here again. So, if I had a diamagnetic core, that means if this medium was diamagnetic, magnetization is like this. For a paramagnetic, M is like this, B and H are like this. In both cases B and H are along the z direction. In this case magnetization is opposite, and so this, remember now that this downward magnetization is actually equivalent to current in the reverse direction, and that current actually produces the magnetic field which is opposite to the direction of the magnetic field produced by the current carrying conductors. In a diamagnetic materials, the magnetization is downward. This downward magnetization generates a magnetic field in this downward direction because of this bound current, and that is opposite to the direction of the magnetic field produced by the current carrying conductor, and so the magnetic field inside the material is slightly less than the magnetic field outside. In paramagnetic materials, the magnetization has the same direction and hence produces the magnetic field in the same direction as the coil, and hence it adds to the magnetic field of the coil, and the magnetic field inside the paramagnetic material is slightly more than the magnetic field outside. And that is the reason why we find that the magnetic field inside the diamagnetic material is slightly reduced, the magnetic field inside the paramagnetic material is slightly increased compared to the airspace. So, let me draw a figure. So, let me draw the cross section. It looks like this. So, this is the material, and suppose this is the coil. So, this is the coil here, and this is the material here. So, let me draw a couple of figures. So, first I want to draw H versus position. So, H is 0 outside, and H is the same everywhere. H is the same inside the dielectric, inside the magnetic material, outside the magnetic material, within the solenoid. It is the same, H is constant everywhere. And if I want to plot B, and if I assume it is paramagnetic, B is 0 outside, B is slightly increased inside compared to outside. So, B inside is slightly more than the B outside in a paramagnetic. In a diamagnetic, B inside will be slightly less than B outside. For a diamagnetic, for a paramagnetic material, it is like this. So, what I have been able to show through a very simple example is that I have been able to use the modified form of Ampere's law to find out what is the magnetic field inside a solenoid which has a core within the solenoid. Our discussion has assumed that the core has a linear susceptibility. I will come to the problem of what happens if the core is made of ferromagnetic materials when we discuss ferromagnetism a little more detail, and that will indicate to me what is the difference between putting a paramagnetic or a diamagnetic material inside and a ferromagnetic material inside. So, this form of Ampere's law which we have been able to write down is a very useful form of Ampere's law. This form of Ampere's law is very useful, and that can help us to, this form is very useful form of Ampere's law, and this form can help us to solve a large number of problems. And in using this formula, all I need to know is the free current that is passing through the circuit, which is what I am passing through the conductors, and the bound currents etc., which are caused by magnetization are contained in the definition of the H vector. And if there is symmetry in my problem, then it is possible to solve the left hand side also and finally calculate the magnetic field, H vector, magnetization and so on. So, the modified form of Ampere's law is very useful. So, what we have done till now is looked at the introduced magnetization as dipole moment per unit volume, showed magnetization leads to a surface current, uniform magnetization leads to a surface current, and that surface current then produces a magnetic field, and the total magnetic field is a sum of the magnetic field that you have generated externally and the magnetic field generated by magnetization of the medium. So, now I want to discuss the different types of materials, different types of media which have magnetic properties. So, as I mentioned before, there are three primary class of magnetic materials: diamagnetic, paramagnetic, and ferromagnetic. Diamagnetic, paramagnetic and ferromagnetic are three types of media which have magnetic properties, which have different magnetic properties, and of course, there are some other materials which we will not discuss in the course here. So, first I want to discuss something about diamagnetic properties, paramagnetism and finally ferromagnetism. Now, what are these diamagnetic materials? You see, atoms, first of all, any matter consists of a large number of atoms, and each atom consists of protons, neutrons and electrons. These electrons are essentially forming orbits around the nucleus, and when electrons have an orbit around the nucleus, as we discussed some time before, this orbital motion gives me a magnetic moment to the electron motion, and that is called the orbital magnetic moment. So, electrons, in my classical picture I will assume that the electrons are spinning, but rotating around the nucleus, but one has to use quantum mechanics to describe the properties. So, I see that the orbital motion or orbital motion of the electrons around the nucleus produces an orbital magnetic moment. As I mentioned before, electrons also have a spin, which is a inherent property of the electron, just like mass and charge, and that spin also has an associated magnetic moment. So, these electrons have both orbital magnetic moments and spin magnetic moments, and the atom consists of a large number of electrons, and so to calculate the total magnetic moment of the atom, I need to add vectorially the magnetic moments of orbital motion and the spin magnetic moments to get the total magnetic moment. Now, it is possible in many atoms that when you add all the magnetic moments of all the constituent electrons, you find that they all cancel each other off. So, with the result that the atom does not possess any intrinsic magnetic moment. Recall our discussion in electrostatics where I had an atom with a nucleus, positively charged nucleus and an electron cloud. The centers of the negative and positive charges, if they match at the center, the electric dipole moment of this is 0. So, the atom does not possess an electric dipole moment. Similarly, here I have atoms in which the magnetic moment is determined by the orbital motion and the spin of the electrons, and the atoms have electrons in such a fashion that when you add up the orbital magnetic moments and spin magnetic moments of all the electrons, what you find is it has no net magnetic moment. So, if you have this material, the atoms are all part of the material here, and the atoms do not have an intrinsic magnetic moment. So, there is no magnetic field associated with this material now. The moment I place this material in a magnetic field, the magnetic field now induces the magnetization in the medium. Now, we will discuss a very important law when we discuss next topic of electromagnetic induction, that there is a law called Lenz's law, and because of Lenz's law, what we find is the magnetization, magnetic dipole moment of these atoms is directed in the direction opposite to the applied magnetic field. So, if I apply magnetic field vertically up, the magnetic dipole moments of the atoms which this induces, the external magnetic field induces magnetic moments of atoms, and those induced magnetic moments are pointing downwards, and this is obtained by Lenz's law, and this magnetic moment now points in the direction opposite to the magnetic field. So, this happens in materials which are called diamagnetic materials. So, diamagnetic materials consist of atoms which have no intrinsic magnetic dipole moment, and when you place this in a external magnetic field, each atom becomes a small dipole, magnetic dipole, and these dipoles are all oriented oppositely directed to the applied magnetic field. And when you remove this magnetic field, external magnetic field, the atoms again lose their dipole moments and they all become again without any dipole moments at all. So, the magnetization generated in these materials depends on the external magnetic field. So, let me write here the atoms no intrinsic dipole moment of constituent atoms dipoles are induced by the external magnetic field induced dipoles directed opposite to external applied magnetic field, and the magnetization disappears when the external field is removed. Now, it is this reason that the dipole moments are pointing in the direction opposite to the magnetic field that the susceptibility is negative, and it is interesting that these diamagnetic materials are pushed from regions of high field to smaller b. In an inhomogeneous field. That is, if you place a diamagnetic material in a magnetic field, in non-uniform magnetic field, they are pushed away from the magnetic field, instead of being attracted, they are pushed away, and that is a very classic diamagnetic material. And this diamagnetism is present actually in all materials and is independent of temperature. So, this is one class of materials which we have discussed today. What I will do in the next class is to discuss the second class of materials called paramagnetic materials and some of their properties, and then we will look at a little more detail of ferromagnetic materials and their properties and how they are able to generate such strong magnetic fields. Thank you very much.